This demonstration consists of 3 ordinary steel wire nails, and they are placed between 2 sheets of super absorbent cloth and connected to a dry cell battery. This connection is through a microammeter so that we can see the current flowing to this nail. This meter is available so that we can check the voltage or potential differences in the various spots on the electrolyte which will be poured onto the superabsorbent cloth. I will now switch on the meters, and you will see that there is no current flowing. As soon as I start to pour ordinary tap water onto the cloth, it provides a conductive path so that the charges can flow from the nail on the left hand side through the charges flow from this nail as the metal is dissolving in the electrolyte through the cloth to this nail. You can see that there is a 6-volt potential which is actually being charged into this nail, and you can see that the voltage between this piece of cloth here and that piece of cloth there is 4.47, and that is due to this piece of cloth being charged up in relation to this piece of cloth by the passage of the electrical energy coming from this nail into this nail. It passes through this nail. So we can examine Faraday's law, we can examine the passage of charges through cloth, through the electrolyte, between a more positively charged piece of steel to a less positively charged piece of steel. Right. You will now see that as I put the contacts closer together, the voltage shown decreases, and this is because the difference in the potential of the electrolyte is different from this position to this position. This is not the metallic part of the circuit, this is the voltage in the electrolytic part of the circuit. You will also notice that the charges pass in all directions. They charge up the cloth here and they charge up the cloth here. Where there is a resistance, you will see that the resistance in this cloth is higher than the resistance in the meter, and therefore they affect the meter readings. Now, the charges will take the line of least resistance, and this area of cloth is charged up more than this area of cloth. So the charges will pass into this nail at that point, and from this nail at this point. So we have a difference in potential of 2.98, 2.9, whereas when we come away from that point, there is an increase because the centre nail is not conducting the charges and bypassing this section of the cloth. So from here to here, the charges have dissipated, and they are 2.37. As we go closer and closer and closer to the nail in the centre, the amount of charges in the cloth reduce because this nail is of equal potential from one end to the other. Now, we can see this by contacting the actual nail as closely as we can, and we will see that there is less than a volt difference, and we are still contacting the actual cloth itself. If we move slightly off of that, we see that the voltage increases. So we're studying the actual conduction of charges through the electrolyte resulting from the power source, which in this case is the difference in potential between this terminal of the battery and that terminal of the battery. Interestingly, these potential differences are caused by corrosion, 4 corrosion cells arranged in series. Each of these cells has a potential difference of 1.5 volts, and therefore 1.5 times 4, as they're connected in series, results in the 6 volts, which is across here, which can be measured quite easily straightly across the nails. Okay, so this will result in 6 volts, 6.68 volts, slightly higher than that because it's a new battery. Right, so now what we will see is the result of this, with this amount of current flowing through the system, and we will see in 2 hours' time, we will see that this nail will have corroded and the corrosion products will be visible. This end of the centre nail will not corrode and it will be clean. This end of this nail, where it touches the cloth, will stain the cloth with corrosion products in the same way that this cloth will be stained by corrosion products. This cloth, however, this nail at this point is protected from corrosion by the charges which are flowing from the battery into this cloth, through this nail and out of this nail, into the cloth round here, and this is at a higher potential than the nail itself. Therefore the charges in the cloth at this point are greater than the charges in the cloth at this point, and therefore greater than the charges in the nail, and therefore the charges are going from here into here, and that will stop any corrosion in this nail. This is cathodically protected. This is the anode of this cathodic protection system, and this nail shows interference. If this was the anode of a pipeline system, cathodic protection system, the charges go to remote Earth, and this is a foreign pipeline, and from remote Earth the charges have a line of least resistance towards, electrically towards, our own protected pipeline. This nail is exactly the same as our protected pipeline. The foreign pipeline will be protected when the charges carry on onto it, and it will corrode accelerated corrosion, known as interference, or stray current, or accelerated corrosion happens on this part of this pipeline because it is close to a coating fault on this part of our pipeline. And that is how cathodic protection and interference current flows. We can use this system to measure the effects on the electrolyte of cathodic protection and of corrosion itself. Now, I've been using the tips of the voltmeter, and I have been using them to touch, to make contact with the electrolyte at various points. Now, it is argued that this is invalid because the electrolyte has a reaction to the tip itself, and therefore what we need to connect to a copper sulfate electrode, and in cathodic protection we traditionally connect this side to the pipeline, which is the protected pipeline, and we can now see that we are making a voltage measurement between the copper sulfate electrode and the pipeline metal. So, when we take this measurement, let's take a close measurement, and we see that we have 2.24 volts, and this will be pipe to soil measurement. This is shown on this meter as positive because I have connected in the way that I have. If I connect these two to the meter in the opposite direction, the same meter, the same measurement, just changing over the polarity of the measuring circuit, you will see it is negative. This is our traditional pipe to soil potential. This is not a potential measurement. This is a voltage. It is the difference between two potentials. It is argued that the potential of the copper to the copper sulfate is a known reaction, and therefore this known reaction being stable, it can be used as a reference potential. When we take the readings, we do not change the point of connection to the pipe. The pipe has an almost infinitely low resistance between one test post and the next. The resistance is 0.006 of an ohm over a mile of 24-inch pipeline. So we can say if we change the connection from one part of the pipe metallic mass to another part, it doesn't affect the reading of the meter. Now, what does affect the reading of the meter is if we move this reference electrode. So therefore, this cannot be a reference electrode. It can only be a ground contact electrode. And you can see that when it is very close to the pipe, it has 1.16 volts. Slightly distant, it is 2.16 and 3.98, 4.94, 6.23, 7.20. So that must be the additional potential of the copper to copper sulfate added to the true potential of the electrolyte to the steel at this point. So, in other words, when we add the half cell, or reference electrode, or copper-copper sulfate electrode to the measuring circuit, all we do, in fact, is alter by inserting an additional potential in the measuring circuit. So if I measure this in relation to that, and then measure that, we will get a slightly lower voltage, 6.82, 6.37, and the voltage when connected to this is 7.24. So that explains what the use of a copper to copper sulfate electrode is when it is used in cathodic protection for measuring the voltage between the pipeline and the electrolyte. So we will now have to leave this experiment for about 2 hours, and then we will be able to actually see the amount of corrosion that is happening. Now during this time, I will add a certain amount more tap water to stop it dropping out, stop it drying out. Now, if you look at the amount of current that we've got flowing at the present, that will change as soon as I put more water onto the system. And the reason why that changes is because there is an increased surface area in contact with the nails, and that lowers the resistance of the charge to the charges that flow through the corrosion cell. Okay? Now, we will not at this stage examine anything further of the voltage, because that's not important, but I will have to leave the ammeter part of the circuit, and I will actually jump that so as to make sure that the ammeter battery doesn't run out and it spoil the experiment. So I will switch this off. I will disconnect from here. I will connect. This directly to the battery. So that the corrosion will continue. You can see the corrosion. You can see that the voltages between the pipe and the soil. You can see that there is a driving force. The energy is flowing through here, through there, through there, through there. When we disconnect this, we can see that all we are detecting is due to the capacitance of the system, and that will be subject to further studies. So we leave it. 6 volts of energy being applied to this nail, and they will cause corrosion on this nail. No corrosion here, corrosion here, no corrosion here. That is corrosion control by cathodic protection.
Thanks for watching. Don't forget to subscribe and hit the notification bell. New videos every week.